Now, looking at shapes and electron geometry, you have two basic types of geometry: electron or electron domain, and molecular. And versus molecular. Now we have a few basic shapes here. Electron domain is where we count only things off center atom. These are going to be either elements or lone pairs. I'm specifically saying elements rather than bonds because single, double, or triple count the same. Single, double, or triple count the same. Let's look at our three structures we did: H, C, N, P, O, 4, and N. We'll do the version with this, NO2. So when it comes to electron domains, how many electron domains do we have on HCN? We'd say 1 and 2. 2 electron domains. It doesn't matter that this is triply bonded to nitrogen. There's only 2. Phosphate. There's 1, 2, 3, 4. It doesn't matter whether we drew it like that or like this. There was 4 things coming off the phosphorus. And this guy would be 1, 2, 3. It doesn't matter whether this was a lone pair or a radical. We'd count that as a third thing coming off this. Now we have our basic shapes. We have, when it has 2, it's linear. 3, it's trigonal planar. 4, it's tetrahedral. 5, it's trigonal bipyramidal. And 6, it's octahedral. So if we're looking just the electron domain, we would call this guy as linear. This guy would be tetrahedral. And this guy would be trigonal planar. Now, when it comes to molecular geometry, we look at only the elements, only the molecules coming off the center. So we'd compare elements versus lone pairs. So the only one that would actually change in this structure would be NO2 because it has one lone pair. Trigonal planar goes to bent. Tetrahedral would go to trigonal pyramidal, and then bent. Trigonal bipyramidal goes to seesaw, T-shape, and then linear. And then octahedral goes square pyramidal. Then square planar. Inner. T-shape, and then linear. Linear. Out of room. I'm out of room, but linear. Typically, we're not going to get to the point where it's linear. But, okay, so we're looking at structures. We're looking at these structures. We need to, if you're given just a structure, if I say xenon chloride, your first thing should not be immediately go, oh, two things, it's linear. You got to look at how many electrons does xenon expect to have. Most of these big structures, you can do this by saying xenon is expected to have 8 electrons. So if I take xenon, take 2 electrons to make its 2 bonds, that's 2 out of its 8. It's 2 out of its 8. So the remaining electrons would have to go into lone pairs. That's 4, 6, 8. So how many things does xenon chloride actually have? 1, 2, 3, 4, 5. It'd be trigonal bipyramidal, 1 lone pair, 2 lone pair, 3 lone pair. So this one turns out to be linear. It does, in fact, be linear. But had I give, instead of xenon, selenium chloride would expect to have 6 electrons. Doing the same thing. We use 2 of the 6, and then we go 1, 2, 3, 4. That's 5, 6. Selenium chloride would be, well, would be bent. So we have to look at how many electrons do you expect to see? How many electrons do you expect to see? So if it's just 3 atoms and no electrons, it's trigonal planar. But if it's 3 atoms and 4 electrons, it's trigonal bipyramidal. 3 atoms, it could be T-shaped. 3 atoms. Put 3, 3, 4. So you must think about this whenever you just when you see a structure written without a shape. Now, the last thing to note is well, there's a few things left to note. I'm going to jump into it, but if you're determining whether a molecule is polar, you need a polar shape and a polar bond. If all atoms the same, it makes it really hard to be polar, especially when we have, I'm going to mark the molecules that if all atoms the same, they can never be polar. If all atoms are the same, this guy, this guy, this guy. If all atoms are the same, all of the base electron domain geometries, square planar, and are linears. If all atoms are the same, these guys can never be polar because the whole fact of polarity requires 2 sides of the same coin to be canceled out, to not be canceled out. So this guy is tetrahedral. Even though the PO bond is polar, all atoms, oxygens, are the same. And so all atoms cancel each other out because this is tetrahedral. It is not polar. Now this guy is linear. So you'd think it's not polar, but we have 1 polar bond. All atoms are not the same. C and N, we have an N. It is probably polar. It's not countered by another N, so it is likely polar. Now this guy, all atoms are the same, but it adopts not trigonal planar, but bent geometry. So we have a O and it's bent, so it's polar. So what I'm saying is like, so square planar. Let's look at a square planar compound real quick. If I said like radon with chloride, 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 lone pair, this chloride cancels that chloride. This chloride cancels that chloride. It is not polar. However, if I did that same structure, but instead of 4 chlorides, I did 2 chlorides, 2 fluorides, this guy does not cancel this guy. This guy does not cancel this guy. And so we have a net dipole poling towards the stronger atom, the fluorines. So that's what I'm saying. If all atoms are the same, square planar is bad. If atoms are different, square planar can be good. It takes a little bit of thought. The last 2 things to really think about here is hybridization and sigma and pi bonding. Hybridization has to do with the shape. These orbitals are made up of S and P in order to make these shapes. We cannot use a standard S or a standard P to make these funny shapes, so we need hybrid orbitals. But the easiest way to do this is all linear, all 2 electron domains are S and P. They use 1 S, 1 P. All things that have trigonal planar or bent in this way, SP2, use 1 S and 2 P. Everything that's 4, so trigonal tetrahedral, trigonal pyramidal, and bent are SP3. Now, since we've run out of all of our P's, we have to go into the D, SP3D, and then we go finally SP3D2 for our octahedral. So octahedral, square pyramidal, square planar, and this version of T-shape would be SP3D. But to do a problem like that, you might have to draw it out. So this guy, radon tetrachloride, with 1, 2, 3, 4, 5, 6 things. So I need 1 S, or 3 P's, and 2 D's. 1 plus 3 plus 2 is 6. 6 electron domains. I need a hybridization that has 6. Finally, sigma and pi. Sigma is the first initial bond. It's a single bond, but I want to say it's the first initial bond between 2 elements. Because the pi bond is additional bonds. Every additional bond between 2 elements is going to be a pi. It's going to be the double. It's going to be the triple. So let's just look at our 3 structures up there. H, C triple bond N. That has 1 sigma there and 1 sigma there. So 2 sigmas. It has a double bond and a triple bond. So HCN would have 2 sigma bonds and 2 pi bonds. Now, phosphate, PO4, has 1, 2, 3, 4 single bonds. So 4 sigma and 1 additional pi bond. NO2 has 2 sigma bonds, 1 pi bond. And when we talk about sigma and pi, we do not pay attention to the electrons. We own the lone pairs. We only care about the bonds themselves. So just because this guy has 3 things coming off of it, we only consider the elements when we talk about sigma and pi.